The most basic division of a computer system is between the hardware and the software. Hardware is often described as the physical parts of a computer that you can actually touch with your hands, although that is not recommended, especially when the power is on. Software includes all the programmed instructions in a computer. There is the main program, called the system software, also known as the operating system, which controls and interacts with the hardware and software components. Application software are programs like Photoshop, Internet Explorer, and World of Warcraft. The main hardware components include the CPU, or Central Processing Unit, main memory, secondary storage devices, and the input and output devices. The CPU is a microchip that receives and decodes instructions from memory. Within the CPU are specialized units. One is the arithmetic logic unit. This part performs operations with numbers. The control unit manages the flow of instructions in time with the CPU clock. The faster the CPU clock, the more instructions that can be processed at a time. The processor I have is a quad-core. That means that there are 4 copies of the same transistor circuitry within one chip. With 4 cores, my processor can execute 4 times as many instructions at a time than if it only had 1 core. The main memory is volatile. That means whatever data is held here would be lost if the power went off. Volatile memory needs a constant flow of electricity to work, so it's only used for instructions in active use. Otherwise, data is stored in a permanent storage device like the hard drive. The main memory can be imagined as a sequence of cells that are either empty or contain instructions or data. Each cell has its own unique address. In the actual hardware, electrical signals of on and off represent all computer information. These on and off signals are called bits. The hardware of a computer is like a kitchen. It includes all the equipment necessary for cooking food, as well as an energy source and location for performing the processes of cooking. The kitchen is where the ideas of a recipe are translated into edible meals. A recipe is like software. A recipe is just a series of written instructions that tell you how to turn raw ingredients into a culinary masterpiece. By itself, a recipe is a useless piece of writing, but as soon as the recipe is interpreted and executed, the recipe has value as a functional tool that can be used again and again to produce the same result. Software is reusable. The instructions of software control the flow of data.
In this video we explore the key component of a computer system, the central processing unit. A computer is defined as an electronic device that takes an input, processes data and delivers an output. To process data, a computer follows a set of instructions, known as a computer program. If we take the lid off a typical desktop computer, we can identify 2 critical components: the memory, that stores the program, and the central processing unit, underneath this big fan, or processor, that carries out the instructions. The earliest computing machines had fixed programs. For example, a desktop calculator is a fixed program computer. It can do mathematics but cannot be used for any other purpose. Changing a program of a fixed program machine requires rewiring or redesigning the machine. A stored program computer is one that has changeable programs. In 1945, the mathematician and physicist John von Neumann described the first design for modern computers that had stored programs. This way of designing computers became known as the von Neumann architecture. The von Neumann architecture has key characteristics. It has a central processing unit with a single control unit. Inside it has an arithmetic logic unit and processor registers. Small high-speed memory that helps the control of instructions and data around the CPU. A von Neumann architecture fetches instructions from memory, decodes and executes them. The von Neumann architecture is not the most efficient design for processing, but it was simple. Programs are made up of sequences of instructions stored in the main memory outside the CPU. They are fetched one by one to the registers for processing. Let's have a closer look at the memory. You will notice that each instruction is stored in a location in the memory. Each location has an address. Therefore, the processor can fetch an instruction stored in memory address 1, for example. So let's summarise to this point. The purpose of the processor, or CPU, is to fetch and execute instructions. The CPU consists of the following components: an arithmetic logic unit, or ALU, that performs calculations and logical decisions, a control unit that sends signals to control how data moves around the CPU, a cache provides fast access to frequently used instructions and data, registers, the program counter, or PC, holds the address of the next instruction in memory, the memory address register, or MAR, holds the address of where data is to be fetched or stored. The memory data register, MDR, holds the data fetched from or to be written to the memory. The accumulator holds the results of the calculations. Computers are complex machines capable of fetching and executing instructions billions of times a second using a very methodical sequence of events inside the CPU. Let's have a look at that sequence in detail. The address in memory of where the next instruction can be found is stored in the program counter. So in this example, in our program, the first instruction is at address 1. Therefore, the value in the program counter would be 1. This is then passed to the memory address register. The instruction is then fetched down into the MDR, which would say load address 5. The program counter now needs to point to the next instruction, which would be 2. Now, a copy of what's just been loaded into the CPU is stored in the cache, so if it's needed again very quickly afterwards, we don't need to go back to the main memory in order to load it again. This makes the computer significantly faster. Now the control unit is going to decode this instruction load 5 and realise that we've got to actually go and fetch a value from address 5 in the memory. So the memory address register is going to change its value to 5, and then we're going to go and we're going to fetch what's in address 5, which is 23, down into the MDR. So the MDR would now contain 23, and we can put a copy in the cache as well, so that we don't need to get that data later again if it's needed very soon afterwards. Unlike the registers, which are being overwritten every time with new data, the cache will be a slightly bigger piece of memory and we'll be able to store multiple instructions and multiple items of data at once. Our value 23 can now be passed into the accumulator. So that's one instruction that has been fetched and executed. Let's just clear the annotations to make the illustration a little simpler to follow and have a look at what happens next. So the program counter is pointing to the address of the next instruction in memory, in this case 2. So 2 is going to get passed into the memory address register and out to the memory, and we can fetch what is in address 2 down into the MDR. So this is add what is in address 6, not add 6, but add what is in address 6. A copy, of course, is stored in our cache, and we need to increment our program counter so that becomes 3. So we need to add what is in address 6. The control unit then is going to pass address 6 to the memory address register, go and fetch what is in address 6, which in this case is the number 12. That's going to come down into our MDR and into our cache. So we're going to add 12 to 23. So the arithmetic logic unit performs the calculation. So in this case we're going to get the answer 35, and the result is stored in the accumulator. So that's our second instruction fetched. We're now ready to move on to the third instruction. So the program counter has the value 3. So that gets passed into the memory address register and then goes out to the memory, and what is in address 3, store in address 6, gets passed down into our memory data register. So store 6, we'll keep a copy in the cache, and we'll increment our program counter to 4. So the control unit is going to look at this instruction, store in address 6, is going to change the memory address register to 6, and then the value that's in the accumulator, the 35, is going to go back to the memory data register and then out to memory address 6. So what was in address 6, which is 12, is no longer there, it gets overwritten by the value 35. We would also want to be storing a copy in our cache just in case we need it very soon later. So the program counter contains the address of the next instruction, 4, so that gets passed over to the memory address register, out to the memory, and we find our instruction. That comes down into the memory data register, and we need to increment our program counter. Now the control unit is going to decode that instruction, end, realise that's the end of the program, and that's it. So in summary, the program counter holds the address of the next instruction. This is passed to the memory address register. The contents of the memory is passed to the memory data register, and we need to increment the program counter to the address of the next instruction. The value may be passed to the accumulator if it's needed by the arithmetic logic unit.